Next, we turn to pipe standards.
Now, I would like to introduce pipe data, specifically regarding the identification, wall thickness, and weights of carbon steel, alloy steel, and stainless steel pipes. The identification information, wall thickness, and weight values organized in this table are all extracted from the ASME B.20.1 and B.20.19 standards. To clarify the abbreviations appearing in the table, STD stands for standard pipe, XS means extra strong, and XXS refers to double extra strong pipe. Weight is expressed in lb/ft, or pounds per foot. One useful point is that the transverse internal area values listed in SQ feet also represent the volume in cubic feet per foot of pipe length.
Let's look at the main items that make up this table. The first part of the table is the identification section, which indicates strength grades such as STD, XS, and XXS mentioned earlier. Next, the nominal pipe size is presented in inches. Then, the wall thickness is denoted by the symbol T. This wall thickness T value is directly linked to the strength grade of the pipe, and the thickness of each pipe is determined by the combination of the nominal size and the identification grade.
Continuing, let's examine the link between the wall thickness T value and the nominal size. Wall thickness is a key dimension represented by the symbol T and corresponds to the nominal size expressed in inches. The important point here is that even for pipes with the same nominal size, this T value varies depending on the strength grade, such as STD, XS, or XXS. Since this wall thickness value, along with the outside diameter, serves as the basis for calculating the inside diameter and internal area, it is an item that must be checked when reading pipe data.
In this section, I want to introduce the nominal pipe size and wall thickness, which are the core identification items in the pipe data table on page 251. In the identification area on the far left of the table, the nominal pipe size is indicated in inches. It is important to note that this is a nominal dimension used to identify the pipe and differs from the actual outside diameter. Next to it, the wall thickness is denoted by the symbol T and is also given in inches. This wall thickness T varies according to the schedule number. For the same nominal pipe size, as the schedule increases, the wall thickness T increases and the inside diameter becomes smaller. Additionally, this thickness value is used as a basic input variable for calculating the metal cross-sectional area or pipe weight. Please also keep in mind that this entire table applies broadly to carbon steel, alloy steel, and stainless steel pipes.
Next, I will introduce the outside diameter column of the pipe data table. The outside diameter is expressed in inches. One point that must be emphasized is that for the same nominal pipe size, the outside diameter remains constant regardless of the schedule. Because the outside diameter is fixed this way, as the wall thickness, T, increases, the internal space decreases, resulting in a reduction of the inside diameter. In terms of a formula, if you subtract the wall thickness, T, twice from the outside diameter, D, in other words, D minus 2T, you get the inside diameter, D. This outside diameter value is used as the reference dimension when connecting pipes or selecting flanges and fittings. I emphasize that you must check the outside diameter value separately in the table, especially for smaller sizes, because there is a significant difference between the nominal pipe size and the actual outside diameter.
Finally, I will explain how to actually utilize the outside diameter column, focusing on dimensional interpretation by schedule and cross-sectional calculations. This outside diameter column is provided in inches and is read alongside the schedule number distinctions for stainless steel and iron pipes. As mentioned previously, the outside diameter D is fixed regardless of the schedule number and has the same value for grades such as STD, standard, or XS, extra strong. Based on this outside diameter, the internal cross-sectional area is calculated as pi divided by 4 times d squared, where d is the inside diameter calculated as d minus 2t. Also, the area of metal is calculated by subtracting the internal cross-sectional area from the total area based on the outside diameter. In this way, by using the outside diameter and wall thickness t together, you can calculate the cross-sectional area, weight, and internal area. When using the table, you should first determine the nominal pipe size, then select the schedule, and finally read the corresponding outside diameter and wall thickness values.
This slide is a reference table summarizing the wall thickness data by schedule for a 16 inches nominal diameter pipe. While the outside diameter is constant at 16.000 inches, it shows the principle that thickness varies depending on the material and schedule number. For example, depending on the selected schedule, such as 5S for stainless steel or STD for iron steel, the thickness is defined variously from 0.165 to 1.594 inches. As the schedule number increases, the wall thickness becomes thicker, the inside diameter narrows, and the pressure rating increases. So please select and utilize the appropriate schedule for your design conditions. Please note that the dashed lines in the table indicate items for which standard values are not defined.
Next, I would like to introduce the cross-sectional area items provided in the pipe table. In addition to the thickness and outside diameter seen previously, this table covers two types of cross-sectional areas, the transverse internal area and the area of metal. The transverse internal area refers to the cross-sectional area of the internal passage through which the fluid actually flows, and it is used directly when calculating flow velocity and flow rate. On the other hand, the area of metal is the cross-sectional area of the metal part forming the pipe wall, used when considering the weight or strength per unit length of the pipe. Interestingly, adding these two cross-sectional areas results in the total cross-sectional area of the circle based on the outside diameter. Therefore, it is useful to know that if you know one value, you can complementarily find the other.
Continuing, I will introduce the unit standards for the cross-sectional area. Both the transverse internal area and the area of metal organized in the table are expressed in square inches. The transverse internal area is the area of a circle based on the inside diameter, and the area of metal corresponds to the area of the circle based on the outside diameter minus the area of the circle based on the inside diameter. Therefore, as the schedule number increases and the wall thickness becomes thicker, the internal area gradually decreases, while the area of metal conversely increases. By using these square inch values as they are, you can process flow rate calculations, pressure loss calculations, and pipe weight calculations using consistent units. However, since errors may occur when mixing with other unit systems, I recommend verifying that the units are in square inches before applying the area values.
This slide shows the area of metal column from the pipe data table extracted from page 251 of the Fisher Handbook. This represents the metal area of the pipe wall in square inches and is an essential material property for stress analysis or thermal expansion review. For example, in the case of a 16 inches nominal pipe, you can see that the area of metal value varies depending on the selected schedule number. For the remaining detailed figures, engineers should first select the schedule number that fits their design conditions and then refer to the value in the corresponding row for weight calculations or structural analysis.
In this slide, we will look at the water weight and inside diameter items, which are the basis of pipe design. Water weight is the weight of water filling the inside of the pipe per foot, expressed in pounds, and the inside diameter refers to the inner diameter of the pipe, denoted by the symbol D. For example, in the case of a 16 inches pipe, the inside diameter varies from 15.670 inches to 12.812 inches, depending on the schedule, showing the characteristic that the inside diameter becomes smaller as the wall becomes thicker. Please refer to the remaining figures in the table directly according to your design conditions. Since these values are essential when designing pipe supports or calculating fluid holdup, I recommend matching and applying the accurate values according to the pipe size and schedule.
This slide is a reference table showing the units and determination principles for the inside diameter, or D, of a pipe. For example, in the case of a 16 inches nominal pipe, the actual inside diameter is the value obtained by subtracting the wall thickness T for each schedule from the outside diameter of 16.000 inches. As the wall thickness increases from 0.165 inches to 1.594 inches, the inside diameter gradually decreases. Since the nominal diameter and the actual inside diameter are different, please be sure to find and apply the actual inside diameter value for the corresponding schedule from this table when calculating flow rate or pressure loss.
Now, I would like to introduce the inside diameter column among the column configurations of the pipe data table. The unit for this column is inches, and the inside diameter is denoted by the symbol D in the body of the table. The same table also presents a water weight column, which indicates the weight of water per unit length, with the unit being pounds per foot. The inside diameter is the most fundamental dimension that determines the flow cross-section inside the pipe, and all subsequent calculations, including cross-sectional area and volume, start from this value.
This table is a reference that summarizes the correlation between the inside diameter, cross-sectional area, water weight, and pipe weight. For example, when the inside diameter is 15.670 inches, the cross-sectional area is 1.33926 square feet, and you can see that if the inside diameter decreases to 12.812 inches, the cross-sectional area also decreases to 0.89529 square feet. However, please note that even within the same inside diameter range, the pipe weight can increase up to 245.25 pounds per feet, depending on the wall thickness. Please check the detailed figures in the table according to your design conditions and utilize them for the necessary pipe specifications and load calculations.
This table contains the specifications and notation conventions for pipes based on the ASME B.20.1.1 and B.20.1.9 standards. For instance, you can see that for the same diameter, the wall thickness and weight increase as you move from STD to XS or XXS. Additionally, the internal area value in square feet is identical to the volume value in cubic feet per foot of pipe length, allowing you to immediately calculate the internal volume. Since detailed figures vary depending on design conditions, please first select the material and thickness grade of the required specification, and then refer to the corresponding values for your design.
Now, I would like to introduce other column configurations of the pipe data table: identification, nominal pipe size, and wall thickness. The unit for nominal pipe size is inches, and the identification column lists grades such as standard, extra strong, and double extra strong, or schedule numbers. It is important to note that the nominal size is not exactly the same as the actual inside or outside diameter, but is a nominal reference size used to name the pipe. Wall thickness is denoted by the symbol T in the table. Even for the same nominal size, the wall thickness varies by grade, which in turn determines the inside diameter and the weight per unit length.
I will now introduce the wall thickness item in the piping data table. In English, it is called wall thickness, and it is denoted by the variable symbol T in the table. The unit is inches. This wall thickness, T, is the most critical dimension that connects the outside diameter and the inside diameter, D, of the pipe. The inside diameter, D, is calculated by subtracting twice the wall thickness, T, from the outside diameter, meaning D equals OD minus 2T. Therefore, even for the same nominal diameter, if the schedule number changes, the wall thickness, T, changes, and the inside diameter changes accordingly. As the T value increases, the inside diameter decreases, while the metal weight per unit length and the strength of the pipe increase. This T column serves as the basic input value when calculating the cross-sectional area, pipe weight, and internal fluid volume.
Next, I would like to introduce the header part of the table that shows the nominal diameter and wall thickness together. Nominal diameter is referred to as nominal pipe size, and wall thickness is denoted by the variable symbol T, both of which use inches as their unit. What you should be careful about here is that the nominal diameter is merely a reference dimension for classifying pipes and is a nominal size that is not exactly the same as the actual outside diameter. Within a single row with the same nominal diameter, different T values are listed by schedule to distinguish the thickness grades. Once the combination of nominal diameter and T is determined, the inside diameter, D cross-sectional area, and weight per unit length are all determined within that row. Therefore, when reading the table, you should first find the corresponding row by nominal diameter, and then select the wall thickness T by looking at the schedule.
Finally, I would like to introduce the outside diameter item of the pipe. In English, it is called outside diameter, commonly abbreviated as OD, and the unit is inches. The most important characteristic of the outside diameter is that it is a reference dimension that remains constant regardless of the schedule number within the same nominal diameter. In other words, even if the wall thickness T changes, the outside diameter OD remains fixed, and instead, the inside diameter D changes. This relationship is exactly D equals OD minus 2T. Furthermore, the outside diameter is very important in practice because it serves as the standard for determining whether the dimensions of externally coupled components, such as flanges, fittings, and valve connections, match. In the table, this OD column is a core dimension item that forms a row together with the nominal diameter, wall thickness, and inside diameter.
Now, I will introduce the outside diameter column in the piping data table. This column represents the outer diameter of the pipe in inches. The most important feature of the outside diameter is that once the nominal pipe size is determined, that value is fixed. For the same nominal size, the outside diameter remains the same even if the schedule or wall thickness grade changes. However, as the wall thickness T becomes thicker, the material fills in toward the inside, so the inside diameter D decreases. This entire table covers carbon steel, alloy steel, and stainless steel pipes, and the identification information, wall thickness, and weight values are extracted from the ASME B.20.1 and B.36.19 standards. The outside diameter column becomes the core input value that serves as the basis for the subsequent calculations of metal cross-sectional area, weight, and inside diameter.
This slide contains the outside diameter and wall thickness data by schedule for an 18 inches nominal pipe, demonstrating the principle that the outside diameter remains fixed while only the wall thickness changes according to the schedule. For example, the standard grade STD corresponds to a wall thickness of 0.375 inches, and the extra strong grade XS corresponds to 0.500 inches. The remaining figures are listed in detail so that you can select them according to your design conditions. Engineers should first verify the nominal size and outside diameter, then select the schedule that matches the required pressure rating and refer to the corresponding wall thickness value.
Now, I would like to introduce the area of metal column in the piping data table. The area of metal is the cross-sectional area occupied by the pipe wall itself, expressed in square inches. Conceptually, it is the total cross-sectional area based on the outside diameter minus the internal cross-sectional area where the fluid flows. In other words, the area of the actual steel. Therefore, as the wall thickness, T, increases, the area of metal increases, which directly leads to an increase in the pipe weight per unit length, or the LB/FT value. For reference, the transverse internal area values marked as SQ.feet in this table also simultaneously represent the volume in cubic feet per foot of pipe length. The area of metal is critical data that serves as the basis for evaluating pipe strength and weight, as well as calculating stress.
Next, I will introduce two columns related to cross-sectional area in the pipe data table. Both are measured in square inches. First, the transverse internal area refers to the area of the cross-section where the fluid actually flows inside the pipe. This value is a key figure when calculating flow rate and velocity. Second, the area of metal is the cross-sectional area occupied by the pipe wall, calculated by subtracting the internal cross-sectional area from the total cross-sectional area based on the outside diameter. This area is used to determine the strength of the pipe, or its weight per unit length. Adding these two areas together gives the total cross-sectional area based on the outside diameter. Please keep in mind that for the same nominal pipe size, if the schedule, meaning the wall thickness, changes, the internal area decreases and the metal area increases.
Continuing with the same pipe data table, I would like to explain the area of metal column in more detail. The unit is also square inches. This value represents the cross-sectional area occupied by the pipe wall thickness. It is calculated by subtracting the internal cross-sectional area from the external cross-sectional area. Expressed as a formula, it is pi divided by 4, multiplied by the quantity of the outside diameter squared minus the inside diameter squared. The larger the area of metal, the thicker and heavier the pipe is, and consequently, its ability to withstand pressure increases. Additionally, this value serves as the basic data for estimating the pipe weight per unit length. In the table, these areas are organized by nominal size and schedule, allowing you to quickly find the necessary values during design.
Finally, I will introduce the section of the pipe data table where several columns are grouped together. This section includes 3 items: area, water weight, and inside diameter. First, area refers to the internal cross-sectional area or the area of metal discussed previously, with units in square inches. Next, water weight is expressed in lb/ft of pipe, representing the weight in pounds when 1 foot of pipe is completely filled with water. This value is obtained by multiplying the internal cross-sectional area by the density of water and is used to calculate the water-filled load per unit length. Lastly, the inside diameter, denoted by the symbol d, serves as the basis for calculating the flow cross-section and velocity. These 3 values are widely used in practical applications such as piping support design, load calculations during hydrostatic testing, and flow rate calculations.
Now, let's look at the inside diameter item in the piping data table. This column represents the inner diameter of the pipe, or the inside diameter, measured in inches. In the table, it is denoted by the lowercase letter d, which refers to the inner diameter of the pipe cross-section. The d value is not just a simple dimension. It is very important because other calculated values in the table, such as the cross-sectional area, water weight per unit length, and area of metal, are all derived based on this inside diameter. For reference, this entire table contains data for carbon steel, alloy steel, and stainless steel piping taken from the ASME B.20.1 and B.36.19 standards.
Next, I will introduce the water weight and inside diameter items in the table. Water weight refers to the weight of the water filling the pipe per unit length. The unit is lb/ft pipe, meaning pounds per foot of pipe. The inside diameter in the same row is denoted by lowercase d and is measured in inches. As the inside diameter increases, the amount of water it can hold increases, so the water weight value also increases. This water weight value is used in practice to calculate the total weight when the pipe is full of water, or to determine the support load for the piping.
This slide is a reference table summarizing the transverse internal area and water weight values for large diameter pipes ranging from 14 to 17 inches in inside diameter. It shows how the cross-sectional area and water weight fluctuate as the inside diameter, d, decreases from 17.670 to 14.438 inches. For example, the cross-sectional area value of 1.7095 square feet is identical to the volume in cubic feet per foot of pipe length, and the corresponding water weight is calculated as 9.245 pounds per feet. Since not all values are listed, please first locate the required inside diameter value during actual design, and then check and apply the corresponding cross-sectional area and water weight values in order.